All right, so let's take a look at this one. Like I said a couple weeks ago when we did this, I like to start off with some dotted lines there just to divide the graph. But do make sure that you erase those afterwards, and you don't have to do that. So, and then I like to label down here where everything goes because sometimes it's a little tricky to keep looking back and forth. So we're going to graph -4 on that part of the graph there. We're going to graph x minus 2 in this middle part of the graph, and then we're going to graph -2x plus 4 on the right part of the graph right there. When we graph -4, what does that look like? Yeah, that's a horizontal line. So remember that just because we see -4, it's f of x equals -4, which is the same as saying y equals -4. So a horizontal line. And that's everywhere that x is less than -2. So it's going to be pointing forever in that direction. I don't know why the line just jumped up right there at the end. Here we go. And it's less than or equal to, so we need a closed circle. Okay. X minus 2, y-intercept -2, slope of 1. That's got an open circle there. And it has an open circle here. But right at that point, we just have an open circle with a closed circle basically filling in the open circle. We're never allowed to have two closed circles on top of each other. That would count as failing the vertical line test. But we can have it work like this. And then last but not least, we have 2x plus 4. So what I like to do is just go up to 4 and then kind of count the slope of -2 from there. And then I'm only going to graph this part of it because the y-intercept would not be part of the graph. So then I'll just erase those right there. And so again, we also have a closed circle filling up an open circle. So that means this graph is continuous. That is a topic that we'll come back to later, but it's also one that you've seen before. There's no breaks or gaps. And that becomes a really important topic in calculus as well. So we'll talk about more about that in our limits unit, but it's still important to remember it. Okay, so basically today we're just going to look at some more piecewise graphs, except you can see from these equations that they're all just a little bit more difficult. But it's the same idea. Like in this graph right here, we have a parabola that we're going to graph on one part, an absolute value graph we're going to graph in the middle, and then another parabola that we're going to graph on the far right part of the graph. Something to remember is that this graph right here is a parabola shifted which way? Left. And that has nothing to do with the x less than -4. So this parabola is shifted left. Without the piecewise graph, it would look like this. 1, 2, 3, 4, 5. Remember with the parabola, you can graph it as like going up 1, up 3, up 5 if there's no vertical stretch on it. That's a way you can do the dots quickly. And that's what our parabola looks like when it's shifted left, 6. Because this one is in a piecewise graph, we will just see the part of it that's less than -4. But sometimes students get confused. These have nothing to do with the shifts. They're just the part of the graph that we see. Okay. So you guys do the next two pieces of that graph. I should end with an open circle here. I just need to fix that. Your neighbor? All right, let's take a look. So this second graph here is going to be between 0 and -4, and we're graphing the absolute value graph. So which way is this graph shifting? Left, how many? 1, and then up or down?
Down.
Down, 4. Okay. And then with that negative out front, what's that graph going to be shaped like? Show me with your hands.
Wait, isn't the 4 the part of the, like, where it is side?
Oh, yeah, you're right. The 4, okay, that is confusing. There's more space in between the functions on the test. Trust me, I spaced it out. Okay, so we're just going left one. Thank you, good catch. With that negative sign out front, what is this graph going to be shaped like? Yes. So we've got this kind of shape to it. So we're just going left one, and the slope on both sides is 1 and -1. So without being a piecewise graph, it would kind of look like this. And like this, and it would go, you know, on forever. Since this is a piecewise graph, and since we're only supposed to be between -4 and 0, we just want that part. We only want to go right there and right there. And at 0, we would have an open circle, and at -4, we would have a closed circle. Okay. Then we're graphing this parabola. What shape is that parabola going to have if it's 4 minus x squared? Show me. Yeah, it's going to look like this. So is that shifted up or down? Up, yeah. This is the same as, sometimes this format can be a little confusing. It's the same as -x squared plus 4. So we're going up 4, and then we're going graphing it downward. So without it being a piecewise graph, it would look like this. And so we would have this parabola right there in the middle of our graph. This is a piecewise graph, so of course we're not going to have all that. We're just going to have this part of it. So sometimes I do find it helpful to graph the whole shape and then erase the parts I don't need. Sometimes that can also get confusing if there's too many lines going on, but it's just a good reminder that because of the domain restrictions, we're only going to see half of this parabola, but we still graph it as though we would see the whole thing. This graph is not continuous. It has two places where there are discontinuities, right there and right there. Does anyone remember what those types of discontinuities are called when the graph kind of has a big old gap in it like that? These are called jumps, or jump discontinuities.
There are other kinds of discontinuities.
Yes, there are other kinds. So if you have like a hole in the graph, is either we could call it a hole or a removable discontinuity. Just gotta write it down here. Discontinuity. Or a vertical asymptote. Which is also called an infinite discontinuity. I'm just going to abbreviate it. Okay, so we're gonna, let's see, there's two graphs here, number 3 and number 4. And then down here, number 5 and number 6. I want to look at graphing this one and number 4, because that can be a difficult one to graph. So this is our parent function, 1 over x, which kind of looks like this. And this is one of the parent functions we need to memorize. That's what 1 over x looks like. 3 over x is going to look a little bit different. It's going to have a stretch of 3, which means that instead of it being here at 1, we're going to be up at 3. But it also means we're going to be over there at 3. We kind of get stretched in 2 directions. The way that I like to think about this, the way that I find the most helpful, is making a little table of values. So if I plug in 0 for x, what's 3 divided by 0? That is undefined. What's that going to give us on the graph? Yeah, this will give us a vertical asymptote. So this is one of those times we need to leave the dotted line in the answer. If I plug in 1 for x, what do I get? What's 3 divided by 1? 3. So there's the point 1, 3. What's another point that I could plug in for x that would give me a whole number answer?
3.
Yeah. We would get the point 3, 3, 1. 3 divided by 3 is 1. Okay. And so that gives us this kind of shape right here. There's not really any other values that will give us whole number points besides like decimals. So if we plugged in 1/2, we would get 6. We don't really have to plug that in there, but it looks like that. What other points could we plug in to get some whole number? Not whole numbers, but they would be integers technically.
-1.
Yeah, -1 would give us what?
-2.
Yep. And then one more.
-3.
Yeah. Would give us, yeah. So that's how I deal with those. Those are a little bit harder to stretch, but we can just plug in points. Okay, so that would be the full shape of the graph. Obviously, if we're doing a piecewise function, we can't have that whole shape. we're just going to -3 and +3. And at +3, have an open circle. So that's the part of the piecewise that we're looking at right there. Okay, here's what we're gonna do. You guys are gonna graph the rest of this one and number 3 and number 5 and number 6. You're gonna do the rest of those graphs, and you're gonna do them in groups of 3. Let's take a look. No guarantees that these are perfectly correct because I also had spring break, so I haven't graphed anything since our last class either. And I did these fast, so. But I think they're right. So for number 3, we've got our horizontal line with an open circle at -6. We've got our x cubed function, which is shifted to the left 1. That's not right. That's not right. Okay, so there we go, right away. It's shifted to the left 1, which means I would have this action right here, like that. So it's like my origin is here, and then I've got my 1, 1, and -1, -1, and then I go 2, 8 from there. That's what it should look like. Okay, questions on number 3? All right. Number 4, yes, we had our 3 over x in there already. The line y equals x, slope of 1, y-intercept 0. The full line would look like that. I'm just graphing the part that's less than -3. So I've got an open circle there, slope of 1. And then my square root function is shifted right 3 up 2, so that's right to that point. And then we're graphing the points like 0, 0, 1, 1, 4, 2, and then the next point would be 9, 3. So those are the points of our parent function for square root of x. Questions on that one? All right. Both 5 and 6 are interesting. So, absolute value of x is a vertical stretch. So the full shape would look like this. Whoa, not quite like that. Something more like that. With like a slope of 2 on one side, a slope of -2 on the other side. So it just gets cut off. We only see that upper part right there. Root -x means we have a horizontal flip. So we're just graphing the other way. So I've got my points here at 0, 0, -1, 1, and -4, 2. And we end with an open circle. So if we saw the full graph, it would look like that. Our next point would be -9, 3. And what that means too is we have this big old gap right there. There's just no graph from 0 to 2. That's okay. Our cube root here is going right 2, down 3. So this is kind of our starting point. So we have 1, 1, and then we have 8, 2 right there. If we saw the full graph, it would look like that. But we're just cutting off our graph right there. Questions on that one? All right, and then number 6, also interesting. So we have our absolute value shifted right 3. So if we saw the full graph of that, it would come down here to 3 and go up like that. Instead, we're just making it to these points right there, open circle. When we say something like this, x equals 1, you saw a lot of questions like this on your homework. It just means 1 point. You're just putting 1 point down. So we plug in 1 for x, we get 0. There's just this little guy chilling down there by himself. That's it. It doesn't really matter that it's to the 4th power. It's just, that's the only point we graph. And then 2 root x is our square root graph stretched by 2. So the parent graph would go 0, 0, 1, 1, 4, 2, 9, 3, like that. So you can see all those points, all our y values have been multiplied by 2. So instead of 1, 1, it's 1, 2. Instead of 4, 2, it's 4, 4. Instead of 9, 3, it's 9, 6. But we don't see the very first point because of the domain restriction, so we just start right there. Those two open circles meet, and then our graph just goes up to the right there. Questions? All right. So we're going to look at some of these other types of problems on here. So we'll go back up to the top of that page here. Some function operations. Okay, so when we see something like letter A, g minus f of 10, we've got our graphs here, f of x and g of x. This 10 is telling us the x value. And this g minus f is we are subtracting the y values. So we would say this is like g minus f of 10. But all we do is we go to f of 10 is negative 5. G of 10 is negative 3. And we just subtract them in that order. Negative 3 minus negative 5. And so that equals 2. F times g of 6 is very similar. We are going to multiply the y values at x equals 6. So turn to your neighbor, what would we get? Got it right. 6. Yeah. So it looks like we have negative 5 times 1 should be negative 5. Okay, C and D are getting a little crazier. We're actually going to do D first because even though that looks more complicated, it's not. So what we do is we plug, it says x equals negative 4, we're going to plug that in right there for x. So 3 times g of 2 times f of negative 4 plus 1. And we just work inside out. What is f of negative 4? 1. Yeah, right there. So f of negative 4 is 1, so that means we have 3g of 2 times 1 plus 1. Uh, 2 times 1 plus 1 equals 3, so this is just 3 times g of 3. What is g of 3? 4, yeah. So we just have 3 times 4, and that equals 12. Okay. Letter C. Turn to your neighbor. How do you think we do this? That's f inverse of negative 3. How do you think we find that? Talk about it. It's a good chance to refresh ourselves on inverses.
We could say minus 3 is the y.
Okay, any ideas how we find f inverse of negative 3?
I think it's the minus 3 is the y instead of the x.
Okay, you're saying negative 3 would be the y on what graph?
The f.
Yeah. What's making you say that?
The fact that it's really the only thing, and inverse functions are swapping y and x.
Yeah, that's exactly right. That is exactly right. Nice. So yeah, because we switch x and y for inverses, we do not have the graph of the inverse of f. We just have f. So instead of plugging in negative 3 as an x value, we're plugging in negative 3 as a y value because we're switching the two of those. Very nice.
What if there are multiple at the spot?
Yeah. We can only do this if there's not multiple.
Ah.
Yeah.
So would we write like undefined or?
What would we write? What would we write?
Is it just not going to be on
Or
the
maybe
test?
we would give two answers. Yeah, it won't be on the test.
Okay.
Yeah, you won't have an ambiguous case like that. I guess in calculus we would just find both values or something like
Okay.
that. Yeah. Yeah. Okay, but do you guys see on the graph of f where y equals negative 3? Yeah, it's at x equals 4. So that means this becomes g of 4. Because we would say that f inverse of negative 3 equals 4. Then we just do g of 4 like normal. Then we get 3. And so that's our answer. Okay. Any questions on any of those? All right, let's go to the last page here. And we'll do all these. So remember, something that we also want to be able to do is write equations for graphs. With this first one here, let's just say we want to start like this. F of x equals, we draw our big curly brace like that. We can see we have a closed circle right there, so we know that we're going to say like x less than or equal to 1. And then our other graph is going to be x greater than 1. What we want to notice here with our parabola, we want to notice like kind of the spacing of the points that we have. So I see we have 0, 0, we have 1, 1, we have negative 1, 1, and we have negative 2, 4. And so as I look at those points, like the spacing and the values are the same as like the parent function. So there's no stretch, it hasn't been shifted. This is just x squared. But we have to be ready to see points that look, more like this. And we say, oh, that would be 2x squared if it looked like that. Remember with lines, we can do this two ways here. We can say, that's the point 1, 3. Our slope is 2, so we could just shift a line to the right 1 and up 3, like that. It's basically just taking that point and shifting it right 1 up 3. And the slope I can see is 2. Or this one's very easy to kind of count back and see where the y-intercept would be. And we could just say, oh, this is 2x plus 1. Either way works. You guys do this one right here. Notice there is a horizontal line right there. That's kind of hard to see. So we just write 0. Okay, this is from -5 less than or equal to x. Remember, we can say less than 2, or we could say less than or equal to, sorry, -2, not 2. As long as we have exactly one closed circle at -2. So we could either put it with our 0 graph, or we could put it with the parabola. It doesn't matter. What's the equation of the parabola?
So negative x plus 4.
Negative x squared plus 4?
Yeah.
Yeah. Did anyone write it the other way? 4 minus x squared? The same thing. Tomato, tomato. Doesn't matter. Yeah, shifted up 4. We have our normal spacing here. And so if I do open circle right there, I need to do closed circle here. So -2 is less than or equal to x. And this would be less than or equal to 1. Because I have a closed circle on the other end. What's the equation of that last line segment there? -x plus 3. Nice. So we've got 2 less than x less than or equal to 5. Okay, any questions on that? All right, let's look down at this last section here. We're not going to do all of this, but I want to just emphasize this right here. So if I need to evaluate function, you know, what we're doing here is we're just plugging in, like number 1, we're plugging in 5 for x. In f of x, we have 3 equations. Which one of those should we plug x equals 5 into? First, second, or third? Third, yeah, because why? It's the simplest? Well, the easiest to plug in would be 3, because then you just get 3 no matter what. But no, that's not why we want to plug into the third one. Mo?
I guess because you get a positive number out of the way because of the absolute value bracket.
No, that's not why I want to plug into the third one. Mikey.
Because x is always going to be greater than or equal to 5.
Okay, and if we're plugging in
5.
5, yes. So we need to plug it into the part of the function where x equals 5. X does not equal 5 in this one or this one. It only is 5 for that part of the function. So we want to make sure we use that. So we need to use the part of the function with matching domain. To the x we're plugging in. Probably a shorter way to say that. I'll figure that out during 6th period. Haha. So for number 2, when we're doing g of -1, we look at g of x. Which one of those functions should we plug -1 into? Do you guys see where x equals -1 on there? Second one, right? So we want to make sure we plug in -1 right there. So -1 squared minus 3 is -2. Okay. When we do something like composition of functions, let's look at number 7. So we're doing f of g of 1. That means first plug 1 into which function? F or G? G, yeah, the inside function. Okay? So where G equals 1 is right here. So that becomes 1 minus 3, which is negative 2. So now what we're doing is looking for f of negative 2. We're substituting this inside part with the number negative 2. Now we go to f of x, and we figure out the part of the function where x equals negative 2, and we plug it in there. So it's 2 times negative 8 minus 1, or negative 17. Be our final answer there. And the same would be true, you know, like number 9 is complicated looking, but it's not that bad. We plug 6 into G right there. We get 3, so we plug 3 into H, which would be right there. 3 minus 6 is negative 3, so we plug negative 3 into F, which would be 2 times negative 27 minus 1, so negative 55. We just take the result, plug it in to the right spot, take that result, plug it in. That's how we do that. Okay. Cool.